Welcome. I am Troy Weeks, a PhD student in the Department of Human-Centered Design working under Dr. Thomas Eskridge at Florida Tech. In this presentation, we will explain the first steps of our research into developing a computational model for a humanoid robot to support the cognitive needs of knowledge workers. In the related work, we discuss some research findings on the psychological state of flow, neurofeedback-driven nudges, and human-robot interaction. We present the architecture for a neurofeedback-driven humanoid. A demonstration of the architecture was conducted to analyze the effects of different reward functions. And in the final section of the presentation, we discuss implications of the nudges and conclude with limitations of our research and suggestions for future work. Almost 50% of the workforce in the United States are knowledge workers. Knowledge workers are tasked with the responsibility of performing cognitive work. And here we emphasize non-routine cognitive work, which involves working with new information and solving unstructured problems. Knowledge workers also research and develop to produce knowledge assets that have economic value. They operate with automation and technological tools in order to complete their work. And they deeply immerse themselves into tasks for long periods of time in order to pursue excellence. Our research is centered around the question, can a humanoid robot deliver neurofeedback-driven nudges to support the cognitive needs of knowledge workers by increasing the duration and depth of their cognitive work? And we will seek to do this using a humanoid form factor in order to explore the possibilities of tangible interaction with the humans. In this reinforcement learning control model depiction that we have here, the human is tasked with completing knowledge work tasks. And in so doing, the human receives some type of feedback on their work and performance with the task. The humanoid is responsible for receiving trait information about the human, which would include elements such as their personality type, their skill level and task execution ability, their trust for the automation, as well as their likelihood to experience flow. Once running, the humanoid continuously receives observations of the human state and task state over time. The reward signal is obtained on a basis of readings and how close the human is to flow state, as well as how close the task is to completion. In our research, we model 3 reward functions for this signal. Based on the information process, the humanoid generates the optimal nudge, and the goal of this model is to increase the duration and depth of cognitive work performed by the knowledge workers. So, how can we effectively nudge knowledge workers to help them perform deep work? Deep work in itself is the ability to focus on cognitively demanding tasks without distraction. Knowledge workers tend to be distracted by their email plenty, and it's about 30% of their daily time that's spent attending to email. And another 30% is spent on team communication and other internet activities, like interacting with your social media and searching the internet. Significant amount of time is also spent when the knowledge workers switch between tasks, when they're multitasking and they're going between different contexts. There's additional time that's lost uh, before the interruption because the person has to plan what they're about to do to change the context. And then after the context has switched back to the primary task, there's some accommodation that needs to take place to get bearings as to where they are in the primary task to pick up. And when these periods of shallow work, such as interacting with your teammates and doing the emails and browsing the internet and so forth, when these periods of shallow work and these distractions are decreased, then chances are there'll be more time to focus on the primary tasks and complete more challenging and cognitively demanding tasks, therefore doing more deep work, which is the purpose of this humanoid architecture. The humanoid architecture depicts a layered pipeline approach where we can see the sensor interface. In this specific example, we are receiving an electroencephalogram stream, EEG, coming in from the humans via a headset, and these signals are then classified into mental state and emotional state. There are two classifications of the mental state where the person can be either engaged or disengaged, and the emotional state has three classes, which is either the person is bored, whether they are happy, or if they're anxious. And the flow state is then estimated by a combination of the mental and emotional states and then passed on into the planning and control layer of the pipeline. In the planning and control layer, we have a neurofeedback planner, which would then compute which nudge is optimal and then pass that nudge onto the controller to be effected onto the robot through its interface. In our specific example, we will be using posture, movement of the hands of the robot, as well as speech of the robot to constitute nudges. And we will also be focusing our attention on the planning and control aspects within this paper. We also have some global services that take place in the background, which is logging of the data, the percepts, the predictions, the states, and the nudges, as well as the communication of the signals that are coming in from the sensor interface. In our case, we're using EEG, but we may very well in the future extend this to electrodermal activity, heart rate variability, as well as facial expressions. Now let us take a look at how the robot actually nudges the human into flow. Here we have the task execution ability or skill on the horizontal x-axis, and we have the perceived challenge of the task on the vertical axis. Flow, according to Csikszentmihalyi, a researcher that's renowned in this area, he states that flow is the zone where skill matches the challenge of the task. And that's depicted by this highlighted region here on this graph. Now, if the task is very challenging relative to the skill of the individual, they may experience some level of anxiety. And in that case, they would be situated in that region marked by anxiety. Likewise, if the person is very skilled and the task is very easy, chances are they're going to experience a state of boredom. Now, the objective of the robot is, given a person in a state of anxiety, to suggest to them in one way or another as how to decrease the challenge or to decrease the perception of the challenge in order to enter into the state of flow. Likewise, if the person is in a state of boredom, how can we motivate and encourage that person, spark their curiosity and boost them into a state of flow by suggesting somehow that they increase the challenge? And these are the intention of the nudges. So for our demonstration, we created a synthetic data set from 18 types of knowledge work scenarios. We simulated the emotional state, being bored, anxious, or happy, and then we perturbed the mental state between different types of engagement, whether we kept it fully engaged or fully disengaged, and then some alternating variant of engage and disengage. So, for example, this is a knowledge work scenario here. It shows 45 4-second epochs comprising 3 minutes. And we see the emotional states across this one are predominantly happy with a few scattered patches of boredom and anxiety during the process of this scenario. The mental state, however, has been alternating every 12 seconds from engage to disengage and back engage and so forth, which resulted in this flow state representation for which the humanoid robot would generate its nudges. So the first situation is if we have the human in the state where they're bored and the system is disengaged, these are examples of the nudges that the robot would use. And notice it's the posture and the movement of the hands of the robot, as well as some motivational phrases that the robot will actually speak. We also utilize a Q-learning algorithm, which is based on a lookup table known as a Q table, and it is populated and updated according to this function, which incorporates a reward function for which we've implemented 3 specific reward functions. And you're going to see the results from those 3 functions. Here is the baseline of those results before there was any training of the agent. So here we can see the agent pretty much making random selections, random nudges, depicted by those green arrows. The blue cell is where the robot is currently observing the state of the human, and the orange cell represents the previous observation. Okay, so the green arrow is the nudge, the blue square represents where the observation currently is, and the orange represents where the previous observation was. Now the dotted square represents the previous nudge from the robot. So if it's red, that means that it was incorrect, and if it's green, that means it was a correct nudge. So these are the depictions of the state-based reward function, and the state-based reward function here really doesn't depict much of a difference relative to the baseline. The actions or the nudges that are suggested by the robot appear to be somewhat random, but there is some improvement. The distance-based simulation of the reward function, we can see shorter distances that the nudges are actually being suggested across, as opposed to the longer nudges. Because again, it's the algorithm is now being a bit more conservative in order to get those rewards that are based on the distance. And the fourth set of plots that we have here represent the combo-based reward function, which incorporated 50% weighting from the state and 50% weighting from the distance-based reward functions. And what this combo-based function represents, or what it shows, is combined benefits from the state and the distance-based reward functions, all in one function. Here's a video of the now robot executing some of the nudges according to the state-based reward function, and we discuss the results which were obtained by the demonstration, and we see that every 4 seconds, with the human receiving nudges from the robot, it became a bit repetitive. And even though some of the nudges were silent, the number of nudges was relatively high across the 3-minute scenarios. And therefore, we would want to somehow reduce these nudges. An alternative approach is to only nudge the knowledge worker after a stabilized period of their flow state. So maybe instead of every 4 seconds, we can let the person establish some stability within a state before we actually perform the nudge, as well as if the person dwells in a state of distraction for about 10 seconds or more, then we perform a nudge. And also, after a person completes a task, this may be an opportune time to invite them to a nudge of motivation, of success. Congratulations. And what we've also realized is that the Q-learning algorithm does not account for the non-stationarity within the context, because when we think of a knowledge work scenario during the early morning of the day, we have different behavioral patterns, as well as perceptions of the tasks that we have to undertake relative to in the afternoon. For some persons, this may be pretty consistent, but for others, this may be wide and varied. And therefore, we may need to find other algorithms that can account for these changes in context. In conclusion, we state that our main goal was to develop a computational model that applies human-robot interaction in deep knowledge work domain to augment human performance. And we've started on that, and we're on that direction. The architecture that we've developed offers a lightweight framework for investigating biofeedback and how these different aids can be used to support deep cognitive work. And the framework also helps us to be able to test the efficacy of different nudge regimes in a very cost-effective manner, as well as to be able to determine which nudges are best suited to specific individuals or different profiles of individuals. And overall, we find that the impact of this research is potentially significant in terms of the economic productivity of our knowledge workers, but also in terms of the human element and the social well-being of these knowledge workers as they're able to experience greater levels of success, as well as to be able to stop when necessary and avert effects of burnout and fatigue, to be able to enjoy their lives and be happy as much as possible. So thank you very much for paying attention. We'll now talk about the future work that we have planned. We are going to conduct some real world experiments where we're going to introduce the humanoid and the human into the loop of the experiment and see exactly what the responses of the humans are to this humanoid. You're also going to examine the attention of humans in greater detail, because a person may very well be paying attention and be engaged, but not necessarily on the primary task. And this we need to be able to discern. And to improve accuracy and responsiveness of the agent, we will be doing more work on the feature engineering. We are also going to extend the sensor interface to be able to include multimodal biosignals, as I mentioned, electrodermal activity, heart rate variability, as well as facial expressions. So this is some of the future work that we have planned, and thank you very much for viewing this video, and our contact information is available to you below.